Okay, so now we're going to work to extend these ideas about center of mass from the simple 1 and 2 dimensional systems to a system involving a function. So what exactly are we doing here? Let's say we've got a function f of x that looks something like this, and we're interested in finding the center of mass for, let's say, the area underneath that curve down to the x-axis. So what we're doing here is the textbooks tend to take these little pieces of area and then turn them into these three-dimensional objects they call a lamina of uniform density that looks something like this. Okay. So we've got this 3D object, and I've drawn it so that it's got a uniform height. The key here is that it's uniform density, okay? And then in this case, the center of mass, will be the point in here somewhere that is the balance point for that object, okay? So in place of mass for these problems, we're going to be using density times area. Okay? And the density we're going to represent with the Greek letter rho, and we're going to be multiplying that by the area, and then that should represent the mass of the object. Okay? Now there are, if you get into more sophisticated approaches to this, you'll see problems where the density is not uniform, but rather is a function itself, and then you'll have to go back in and revisit some of these ideas. Okay, so first off, the idea here is that we're going to be doing the same thing. We're going to be doing the sum of the mass times position divided by the sum of the mass. Okay? So, like I was saying, in place of the mass, we're going to be using density times area, and the area is just going to be the area under the curve. Okay? So, let's work our way up to that. So for starters, we're going to do what we always do, which is to chop this up into rectangles. And I think for clarity's sake and the sake of consistency, we're going to choose our x sub i's as the midpoint for these rectangles. Okay? And that'll make things work out pretty nicely. Okay? So there's our x sub 1, x sub 2, and so on. Okay? So for each position here, now here's the other key piece. Now that we've identified these rectangles, now the center of mass for each of these rectangles is, of course, going to be half the width and half the length, right? If you've got a rectangle like this, where this is L and this is W, the center of mass is here, where it's half of the length and half of the width, okay? So we'll come back to that in just one second. Okay, so here's the center of mass for each of these rectangles. And then once we identify the center of mass for each of those rectangles, then we can do the center of mass for all those points and just treat them as points the way that we were doing in the two-dimensional system in that previous section. Okay, so what we need to figure out here is mass, right, which is the density times the area. And so this is going to be density, and then our area is going to be f of x sub I times delta x. Okay? Let's say this is x sub I, and so f of x sub I is the height, delta x is the width. This is just the area that we actually started out with back in winter term. Okay. So then if we take that times the position times x sub I, then what we come out of this with is the sum of all these, let's say, rho x sub I, f of x sub I, delta x, and then we'll sum these up from 1 to n, take the limit as n goes to infinity, and so this is going to be rho times the integral of x times f of x dx. Okay, so let's see here. Yeah, so this is mass times position right here, because there's our position, our x sub I. So this is our mass right here, there's our position. When we turn it into a sum and take the limit as n goes to infinity, that creates the integral. Okay? And then we want to divide that by, and this is going to give us our x bar, we're going to divide that by the sum of the masses, which in this case, mass is going to be just rho f of x sub I delta x. So then if we sum these all up and then take the limit as n goes to infinity, then this will be rho integral f of x dx. And so that's going to make our x bar equal to rho integral x f of x dx divided by rho integral f of x dx. And then our densities cancel out. So as long as this is uniform density, those are going to cancel each other out. And this is often expressed as 1 over the area integral x f of x dx. And this is what you'll see, or what you can see, on your formula sheet. Okay, so this is our x bar formula. Okay, now let's back up and do y bar. All right, let's see here. So we're going to erase this stuff to get the y bar. We need a y here and there. All right, let's see, the mass is not going to change. Let's get in here. Yeah, that's still going to be, we're still going to have the same denominator here. That's going to be rho integral f of x dx. So that's what I'm erasing right here. All right. But what is the numerator going to be? The mass times the position for the y coordinates. Well, I could write y sub I here, but y sub I is really f of x sub I, right? But notice that that's the full height. This is the position that we're interested in right there, and that is 1/2 of that full height. Okay? That's the y coordinate for the center of mass of all these rectangles. Okay, so now we're going to sum these up. We've got the rho, we've got the 1/2, we've got 2 f of x sub i's. So that's going to get squared. And so then when we turn this into an integral, what are we going to get? We're going to get rho integral 1/2 f of x squared dx. So that's going to be our numerator over here. And that's going to be equal to y bar. Again, those uniform densities cancel each other out. And so this is expressed in a similar way to the x bar. We call this 1 over the area. And then integral 1/2 f of x all squared dx. And that's the formula for y bar. That's on the formula sheet. Okay. Let's see here. Now, let's do, what if we want to find the center of mass for something that's between two functions? So now we're going to have an f and a g. So let's back this up here. Let's leave that. So again, our x bar is going to be the mass times position divided by the sum of the masses. Now our diagram is going to be a little different here. We're going to have an f function, and then we're going to have a g function. Okay. Well, the mass we're still going to consider to be the density times the area, but in this case, the area is going to be, the height for those rectangles is going to be f of x sub I minus g of x sub I, and then the width will be delta x. Okay. Let's see here. So let's go ahead and put our rectangles in. Okay, there's our x sub I right there. Okay, so the x position isn't really going to change much. So if we take our mass, f of x sub I, g of x sub I, delta x, the x position is still just going to be x sub I. Okay, and so again, take the limit of the sum of this stuff, delta x, x sub I. Then when we turn this into an integral, we'll have the row integral x times f of x minus g of x dx. Okay, so that's going to go over here in the numerator, row integral x times f minus g dx. And then the denominator is just the integral of f minus g. Right, because that's the area between the two curves, is that integral of f minus g. And again, those densities cancel each other out. And this is again 1 over the area, integral x times f minus g dx. So there's our formula for x bar. If we've got a figure that's between two curves. Okay, one more derivation. Let's see here. Change the numerator. Denominator is going to stay the same. Here, this is going to be y sub I, because now we're doing y bar. Let's see here. So the area stays the same, and it's the position that's going to be different. Okay. So, how is that position going to be different? Well, how do we describe this point that's halfway between there? Because it's no longer just a half of the f function. Let's see here. A half of f minus g is not going to get us where we want to go. I don't know a good way to describe that without a discussion or a give and take. Okay? So if you're thinking that that's going to be half of f minus g is this piece right here. Half of it is going to put you like down here. Okay? What we need is half of f plus g. It's the average, right? If you want to find the average of two quantities, you find half of their sum. That's what this point is right here. That is 1/2 of f plus g, because it's the average of these two function values. That's how you get exactly in the middle of them. Okay? So that's the average of those two function values. That's where the y value for that rectangle is going to be. All right, so now what do we have here? Let's see, we've got the row. We'll put the delta x in a minute. Oh, we're going to need 1/2. And then this becomes f squared minus g squared, right? It's a difference of perfect squares. You've got f plus g times f minus g. I'll put those i's in there. and then delta x, right? This times this is where this f squared minus g squared is coming from. All right, take the limit, and now we'll have an integral of 1/2 f squared minus g squared, and then dx. And that 1/2 is outside the parentheses, okay? It's a half of the difference of those two squares. Okay, so that's what our numerator is going to look like. F squared minus g squared dx. The rows cancel each other out, and then here's the formula that's on your formula sheet. It's the integral, it's 1 over a times the integral of 1/2 f squared minus g squared dx. Okay, well, that's a little bit involved, but again, you've got both of those formulas, whether you're working with the area between two curves or the area between a curve and the x-axis. We've got those formulas on the formula sheet. I know that this is a little confusing, but that's the way it goes. I also want to point out, if you remember a couple videos back, I was talking about how integration is not just the area under the curve. So here's another example of that, okay? We're using integrals to define the center of mass, and you can continue to do that. You can do that for any calculation that you make, right? If you can take something and chop it up into little pieces, take the limit of that sum, then you can make that calculation through an integral. And that's, I think, one of the really amazing things about integral calculus is just how many different things that you can use it for. Okay, let's look at some examples. All right, let's see here. On this handout, we'll start with problem 2 is very, very simple. And in a lot of engineering textbooks, you'll see this just given as a formula, because you can parameterize this. And this is actually very, very typical. Like if you get into engineering, what's called statics, right, is the study of things that aren't moving. And center of mass is a key to one of those. And I've got a couple of statics textbooks, and they've just got a page of formulas for finding center of mass for all these different shapes. And they all come from just parameterizing the shape and then using those integrals. All right, let's see here. Problem 2, we're working with y equals negative x plus 3, and then y equals 0 and x equals 0. So negative x plus 3 is going to look like that. And then y equals 0 is down here, x equals 0 is here. And so we're working with a triangle. Okay, well first let's find the area. I think we know it's going to be 4.5, right? Because it's just a half the base times the height. But let's go ahead and do the integral anyway. Okay, so the integral is going to be from 0 to 3. Our function is negative x plus 3. And so let's see, that's going to be negative x squared over 2 plus 3x from 0 to 3. Negative 9 over 2 plus 9 minus 0. And so there's our 4.5, or 9 over 2. Okay, so now x bar is going to be 1 over a, let's see here, let's put these over here. X bar is 1 over a integral x f of x dx, and then y bar 1 over a integral f of x squared dx. Okay, so 1 over a is the reciprocal of this, so it's 2/9. And then we'll have the integral from 0 to 3, x times f of x dx. All right, so negative x squared plus 3x. And now when we take the integral, 2/9 negative x cubed over 3 plus 3/2 x squared from 0 to 3. All right, let's see here. So this is going to be 2/9 times negative 27 over 3 plus 27 over 2. Well, that's 9. Let's see here. This is 13.5 minus 9 should be 4.5. And this says the x-coordinate will be 1. Okay. Let's see. The y-coordinate's also going to turn out to be 1. But let's go ahead and calculate that. So 1 over the area, 2/9 integral 0 to 3, f of x squared, so this is going to be negative x plus 3 squared dx. So let's square that out, so that'll be x squared minus 6x plus 9. And then if we do the integration, oh, what did I leave out? My formula was wrong. Going too quickly here, right? Because our y-bar formula is 1/2 f of x squared dx. And for those of you who caught that as I was doing it, good for you. All right, let's put the 1/2 in there. There we go. Okay, so then this will be x squared minus 6x plus 9 from 0 to 3. So those 2's cancel. That'll be 1/9. This will be 9 minus 18 plus, let's see. Oh, I didn't even integrate that. Holy cow. Doing poorly today. All right, let's see what we get out of this. Okay, 2/9, 1/2. Now integrate x cubed over 3. This will be 3x squared and 9x from 0 to 3. Okay, let's try this again. 1/9. This will be 27 over 3. Then minus 3 times 9, which is 27, and then plus 9 times 3, which is also 27, and then we've got the minus 0 on the end there. Those cancel out. 9 times 1/9 is equal to 1. And if you look up the formula for the center of mass for a triangle, I'm not sure if it's just a right triangle. I think it's all triangles. It's a third of the height and a third of the base. Okay, well, hopefully I'll do better on the next one. Let's take a look at problem 4. It helps to have the right formulas. So let's leave those up there for now. Because problem 4 is also a area between the curve and the x-axis. Okay, so problem 4 is 1/3 x squared y equals 0, x equals 3. So what does that look like? 1/3 x squared is just kind of a parabola that's opened up like this. Y equals 0 is down here, and then the x equals 3 gives us a place to cut it off. Let's see here. I'm not sure that it matters what that y value is, but is that also 3? Right, because that'll be 9 divided by 3, so that's the 0.33. Okay. So first we need to know the area, right? All right, so our area is going to be the integral from 0 to 3, 1/3 x squared dx. So if we do the integral here, that'll be x cubed over 3 times 1/3. So x cubed over 9 from 0 to 3, 27 over 9 minus 0, so that's going to be 3. Okay, so that's our area inside there is 3 now. So now if we want to find x bar, That's going to be 1 over 3, integral from 0 out to 3, x times 1/3 x squared dx. Okay, so that'll be 1/3 x cubed dx, and then if we do the integration, that'll be x to the 4th over 4 times 1/3, so x to the 4th over 12. So that's 1/3 times 81 over 12 minus 0. So let's see, that's going to give us, what is that, 27? Let's see here. Right, 27 over 12. And then reduce that with the 3 one more time, and that's 9 over 4. 2.25, right about there. Okay, so that's our x bar. Y bar is going to be 1 over a, and then integral 0 to 3, 1/2 f of x squared. Okay, so that's 1 over 6, integral from 0 to 3. This will be 1/9 x to the 4th dx. And you can keep that 1/9 in there, or you can pull it out with the 1/6, however you want to go about doing this. I think I'll move it outside, 1 over 54, and then I'll just have the x to the 4th to integrate, so that'll be x to the 5th over 5. So 1 over 54, let's see, 3 to the 5th is 243 over 5. So let's see here. 54, 9 goes in, oh, well, this is 27 times 2, and 243 is, what is that, 27 times 9? Yeah, okay. And so this is 9 over 10. All right, so our y bar is just a little bit less than 1, and so that'll put it right about there. And this is what I was saying in that last unit when we were talking about the center of mass without the integrals. It's nice that you can kind of eyeball this and get a sense of whether or not your answer makes sense. Okay, the center of mass for this thing is going to be where most of the area is, which is over here. Okay, like if you get an answer for this problem and it puts your center of mass out there somewhere, you know you've made a mistake, and believe me, I've done that in the past. Okay, all right, so that's problem 4. Let's see here. Let's stop here. And then I'll come back, I'll make another video that goes over some problems for an area between two curves, okay? So the quiz that goes along with this video will only cover functions where your area is under the function to the x-axis. I'll come back, I'll make another video with some sample problems that are between two curves, and then there'll be a quiz with that where you've got a question about between two curves. So we'll do that then.